Hello, welcome back. This is Dr. Oz from Washington, Kentucky University. Today we're going to go over an application of integration, which is in fact finding the average value of a function. That involves some integration, and that integration is going to be done through the use of the rule that is developed in this section. And in particular, I'm going to use the U substitution together with the log rule. In particular, I'm going to use U substitution to sort of take care of the integral part of this question. So before we hit the road, let's just read the question statement. It's asking to find the average value of the function for ln x divided by x over the interval 1 and e. And remember that e is a special number, Euler's number, that's 2.71 with a lot of decimal places after that. And I want to show you the definition of the average value of a function on an interval. This was something that we covered in an earlier section. That's why I wanted to recall this definition here. So if you have an integrable function on a closed interval a and b, then the average value of the function on the same interval is 1 over, let me just copy that down here, 1 over b minus a from a to b f of x dx. B in this problem is the right end of the interval, which is e, and then 1 is the left end, so that's exactly what a is. And the limits of the integral would be 1 and e, and the function provided to us is 4 ln x divided by x. And also I want to make a point that the average value of a function comes out of the mean value theorem for integration. Towards the end of the video, I'm going to show you a graphical outlook of what means to have the average value. And here we go. So we have the average value defined through this integral. Our task is to find the value of the definite integral. So for that reason, we're going to use a U substitution. And if you realize that you have ln x here, and ln x has the derivative 1 over x. 1 over x dx can be replaced by du after the U substitution. So to be more specific, why don't we call u to be ln x so that du is equal to u prime dx. And u prime is the derivative of ln x, which is 1 over x. So du turns out to be dx over x. That's good news because I can pull out this 4. And then I have ln x dx over x, and since u equals ln x and dx over x is du, I can convert this integral. To 4 divided by e minus 1 u times du. I just need to worry about the limits, especially when you have U substitution for a definite integral. You can also convert the limits to the new variable. This is us telling that x equals 1 and x equals e because the main variable of the integral is x. So now it's U integral, so this should be u equals something and u equals another thing based on the U substitution that I used. So why don't we just go with replacing the limits. When x equals 1, u is exactly equal to ln 1. By using the U substitution here, that's equal to 0. When x equals e, which is the upper bound, right? So then u is going to be equal to ln of e, but if you use your TI-84, you can check that ln of e is just 1. So now I will replace those limits 1 and e by the new limits written in terms of u. So this is 0 to 1. Okay. By using the fundamental theorem of calculus, we can write this integral as, let me just continue from here, 4 divided by e minus 1, u squared over 2 with the bracket notation. You have the lower limit and upper limit. Okay? All right, so and we know that we're going to plug in the upper limit and the lower limit, but lower limit is 0 when you plug in that for u. That term is going to be just 0, only the upper limit is going to survive, so that you end up having with 4 over 2 times e minus 1. And if you cancel 4 and 2, you have 2 over e minus 1, and that is the average value of the function for ln x over the interval 1 and e. as you see that this is sort of like the use of u substitution for the given integral together with switching the limits of the integral into the ones written for the u substitution. We know that the integral of 4 ln x dx from 1 to e is the area between the curve and the x-axis. Since the function is positive, so the function is about the x-axis, so all the values are positive. So this integral is in fact corresponding to the area of this orange region. Okay? And in the formula of the average value, we divide that area by e minus 1. So what that means is that if you have a function taking the values all the way from 0 to somewhere here, like 1.5-ish, then the average value of the function should be in between 0 and that 1.5. So in other words, you have the function taking the average value to be like 2 over e minus 1, because we calculated this integral, and that's 2 over e minus 1. You can go ahead and then calculate this integral. So this is 2.7 minus 1, so it's almost like 1.7. 2 divided by 1.7, it's somewhere around here. So in other words, the area dividing e minus 1 is in fact the average value of the function. So just think about e minus 1 to be the length of this piece here from the right end to the left end. Let me just show it like this, from the right end to the left end of the region here. And if you multiply this quantity by the average value, that's exactly what the area is defined. So to be specific, I'm talking about that this area can also be represented by the area of a rectangle, and that rectangle has the height exactly equal to 2 over e minus 1, which is the average value of the function. So if you know the average value of the function, that average value, which is the height of the rectangle, times the length of the interval that you do the integration on, is going to be the area of the rectangle. So the original area can be represented by the area of this rectangle. This is in fact an application of the mean value theorem towards finding the average value of a function. I hope this picture helps you to see the relationship between the area and the average value of the given function. All right, this ends the video. Thanks for watching. I'll see you in another video. Bye.